Hello everyone, I'm Mengchun Zhang, one of the TAs for the Fall 2025 Introduction to Deep Learning course. We'll be talking about datasets and data loaders in the next few sessions. Today, I'll walk you through the ideas of datasets and explain why both datasets and data loaders are so essential. So, why do we need datasets and data loaders in the first place? Well, in deep learning, we typically work with large datasets, way too large to fit entirely in memory. Even if we could load them all at once, we'd still need to organize the data, preprocess it, shuffle it, batch it, and often apply custom transformations during training. This is where PyTorch's dataset and dataLoader classes come in. The dataset class defines what the data is and how to access a single sample. The dataLoader defines how to iterate over the data efficiently, handling batching, shuffling, and parallel loading, etc. Here is a simplified pipeline of deep learning training, which closely resembles the structure you'll use in all the Homework P2's notebooks. The dataset and data loader are responsible for the data preparation part of the pipeline. Now, let's zoom in and take a closer look at how things actually work under the hood. So imagine we have a large dataset, each data sample with a unique index. This can be like image label pairs, input-output sequences, or any other format you'll encounter in Homework P2. We wrap this dataset using a custom dataset class, which either stores the data internally or implements logic to load samples dynamically. Typically, we split data into three parts: train, validation, and test. Each split corresponds to a different dataset instance, because we often want to handle them separately. For example, applying different transforms, or not shuffling in the test set. These datasets are then passed to separate data loaders. Again, one for training, one for validation, and one for testing, because we want different loading behaviors as well. For instance, the training loader shuffles and loads batches randomly, while the validation and test loaders usually do not. The data loader batches the samples, shuffles them if needed, and loads them in parallel using multiple workers, which you'll see in more detail in the data loader session. So to make this system work, a custom dataset class needs to define two code functions. The learn tells PyTorch how many samples are there in the dataset. The getItem function fetches and returns the sample at some specific index, for example, an image and its label. Once defined, we pass this dataset into a data loader, which takes over the rest of the work. So how does the data loader actually work with the dataset? It begins by sampling indices. This is handled by a component called the sampler, which is created based on the shuffle flag in the data loader. The sampler determines which data points to fetch next and in what order. These indices are then passed to the dataset and use the getItem function to retrieve each sample accordingly. The retrieved samples are then collected and passed to a function in the data loader called collate function, which arranges them into batches, typically as a single tensor or direct dictionary of tensors. So to summarize, the full data loading process involves what to read, where to read from and how to organize the data, combine the samples. That's a high-level idea of how we can handle data efficiently and flexibly with dataset and data loader. Now, let's go to the notebook and see how we can actually define and implement the dataset. Before diving into the PyTorch dataset class, let's first look at some basic dataset structures, NumPy, pandas, and tensors, which will help us understand and work with data more efficiently. First, NumPy is widely used for storing numeric arrays, like image data or signals. We often save them as NumPy files and load them back with basic file I/O. This is something we'll use in homeworks. For more advanced usage, check the NumPy recitation. Next, we have pandas, which is useful for working with tabular data like CSV. Although we don't use pandas to load raw data in homeworks, we use it to handle predictions or save results for Kaggle submissions. Pandas data frames are structured like dictionaries. Each column is a key value pair, so we need to assign a value to each key, as done in this example. We can then easily save and load them using two-sets way and recitation way. Finally, tensors are the code data structure we'll use for modeling. PyTorch uses 64-bit integers by default, but we can switch to 32-bit floats to save memory. We can set that using the tensor's D type. It's important to know that it's very necessary to stay consistent with data type. Mixing 64-bit and 32-bit may cause errors. Here is some common tensor operations include dot shape to check dimensions, dot reshape and dot view to change shape, and dot t to transpose. For neural networks, one of the most important operations that we use is matrix multiplication, which is done with touch.matmul or the add symbol. One common mistake is confusing matrix multiplication with element-wise multiplication. So the matrix multiplication follows the standard rules from linear algebra. For example, multiplying a 2 by 3 matrix with a 3 by 1. Whereas element-wise multiplication just multiplies matching elements at the same position. Alright, now let's get into the code, the PyTorch dataset class. The PyTorch dataset class is a fundamental building block for preparing and feeding data into deep learning models. You'll use it throughout your homeworks and also in the real-world problems. To define a custom dataset class, you need to implement three required functions. The init function is a constructor. Here you can load data into memory or prepare paths for loading later. The learn function, as shown before, returns the number of samples in the dataset. The getItem function retrieves a single data sample by its index. This is what the data loader calls under the hood. Optionally, you can also define collate function later if you want to customize how batches are formed in a more complex way. We'll cover that more in the data loader session. Now, a few important design tips to keep in mind. If your dataset is small enough to fit in memory, it's faster to load and preprocess everything in the init function. But if you're working with large datasets, it's better to load samples on the fly inside getItem function, even though it's slower, but it saves memory. You should also think about how you instantiate your dataset, whether directly from features and labels or from a directory path that requires loading files. Each approach has its benefit depending on the size and format of your data. For training and testing, it's prudent to define separate dataset classes. The test dataset class might differ since it generally doesn't have access to ground truth labels, which you'll understand more when you go through the examples in the next video. To optimize your workflow, consider initially limiting the number of samples loaded for faster prototyping. Once you confirm your pipeline is functional, you can scale up to the full dataset. I encourage you to take some time reviewing this section in the notebook for more detailed guidance on building your own custom dataset classes. See you in the next session, where we'll working through concrete code example together. Okay, with the dataset concept we just covered in mind, let's look at some examples. Here's a simple recap of what we've discussed. A basic dataset class. We instantiate the class with features and labels, X and Y's. We define learn to return the dataset size, and getItem to fetch data by index. Now, that's how we define dataset for training, where both input and ground truth labels are available. But what about a test dataset? How do we handle that? The key difference is that in a test dataset, we don't expose the labels because ground truth label is not available during inference. So when defining the test dataset class, we still write the init function, but only include X. We do not define or return Y's. Next, let's see how this dataset class works. We first create an instance of the class, then check its learn function. To retrieve a sample, we index it, say dataset 0, which calls the getItem method and returns the corresponding x and y. You can also loop through the dataset or use next to get items one by one. Okay, try this small exercise to get comfortable with how indexing and retrieval works in your customer dataset. Now, let's look at a more realistic example, one based on the Kaggle-style dataset you use in all homework P2s. The Kaggle dataset is divided into three parts: train, validation, and test. Train is used to train the model. This is where the learning happens. Validation is used alongside training to two hyperparameters and monitor model performance. It helps decide where to stop training or which model to keep. Test is used only after training and validation are done to evaluate the final model's performance. So train and validation work together during development, while test is held out for the final evaluation. Another thing to note is that in this init function, we included a class that loads data from a directory structure, instead of x and y stored in memory as shown in the example before. This version reads data from a root folder and processes files as needed. Okay, all this logic is mostly the same, but you need more preprocessing. And the test dataset again has no labels, just like the simple version earlier. Take some time to explore this example in the notebook. It's directly related to what you'll do in the homeworks. Now, let's look at a specific case from Homework 1P2 to give you a more concrete sense of the process. This involves frame-level classification of speech data. We use it to illustrate the general approach to work with datasets, but the first point we want to emphasize isn't about the dataset class itself. That is, before defining your dataset class, you need to understand your data, which means you need to load an example, visualize it, check the shape, and think about how it was generated. It's easy to skip, but this step is very crucial in any real-world deep learning task. So the dataset contains speech recording encoded as MFCCs, short for male frequency spectral coefficients, which are spectral features derived from the raw waveforms. You also get frame-level labels for training. MFCCs can be thought of as a form of feature engineering, where raw audio waveforms are converted into spectral features that better mimic human hearing. We won't go deep into MFCCs here. The write-up and later recitations will explain more, but all you need now is in the notebook. Okay, we'll give you a glimpse of the dataset structure and guide you through loading a single training sample to understand the data. As you can see, after downloading and unzipping the dataset, you will see the following folder structure as we mentioned before. Train Clean 100 contains MFCC data and labels for training. The Dev Clean contains MFCC data and labels for evaluation. The Test Clean with only MFCCs and no labels will be used to grade your model's predictive performance. For each of these datasets, you'll need to construct a custom PyTorch dataset class in your homework. And as we mentioned before, more preprocessing part needs to be handled inside the dataset class. We'll give you a general idea of this preprocessing by taking a look at a single training sample. Here, we load a speech sample from the train folder, along with its corresponding transcript. Each audio sample is stored as a 2D array of shape, t multiply f, where t is the number of time steps and f is the number of features. In our case, it's 28. The corresponding label, a phone-link transcript, is a 1D array of lengths t plus 2. Since it includes two extra time steps, which mark the start of the sequence, SOS, and the end of the sequence tokens, EOS. However, for homework 1, those two tokens are not needed, so your preprocessing should remove them, but they will be useful in future assignments. And also note that each sample represents only 25 milliseconds of speech, which may not be enough to train a model. To address this, you will be asked with creating an adjustable context window of size k around each sample to provide more local information. That's another key idea in this homework. Instead of using just one frame at a time, we concatenate several frames around the target time step. The result is a big feature vector that is better aware of the local information. For example, if we use a context size of 10, each input will include 10 frames before and after the current time step. So a single frame originally shaped 28 becomes 21, 28. And since we are using an MLP, this needs to be flattened before feeding into the network. So we flatten the entire dataset and use it in our MLP model. Okay, that's all the preprocessing we need to consider when defining datasets in homework 1P2. Now, an equally important step is to visualize the dataset. And you should definitely do this before or alongside writing your dataset class. It's very useful for debugging and getting a feel for the data, like understand the data distribution, spot anomalies, and debug transformations like image processing later in this semester. An example is provided to show how to plot an MFCC frame. This is what a data point actually looks like. Note that the MFCC has been flipped and transposed to match the traditional view. X-axis as time, Y-axis as MFCC features, with the zeros MFCC at the bottom. This example uses a context window, so 10 for the past and 10 for the future. That shows how our dataset is structured. Okay, that's it for the recitation. Thank you so much for listening. In the next session, we'll see how to pair this with data loaders and feed the data efficiently into our models.